Imagine you are trying to decide whether to attend an outdoor music festival this weekend. Your brain naturally weighs three simple factors. Is the weather clear? Is the ticket under $100? And is your best friend going? We can represent these as binary inputs, ek and x, valued at 0 or 1. But these factors don't hold equal weight in your mind. If perhaps you hate rain so much that weather is absolutely non-negotiable. To model this, we assign a numerical weight to each input and set a threshold called a bias. If the weighted sum exceeds this bias, you go. If not, you stay home. This simple weight and threshold mechanism, formulated by Frank Rosenblatt in 1958, is the foundational building block of the artificial neuron, or perceptron. Let's look at this decision-making process mathematically as a geometric division of space in a two-dimensional feature space where x represents weather and x represents price. A single perceptron defines a straight decision boundary. The formula list b equals 0 is the equation of a line dividing the plane into two distinct regions, one where the neuron outputs a 1 and one where it outputs a 0. For decades, this elegant simplicity was all a fatal flaw. In 1969, Marvin Minsky, Seymour paper published a famous proof showing that a single perceptron could not even solve the exclusive or XOR problem because the data points could not be separated by a single straight line. This mathematical bottleneck halted neural network research for over a decade in what became known as the first AI winter. To solve complex, nonlinear problems, neural networks had to transition from rigid step functions to smooth, continuous activation functions. The classic step function outputs exactly 0 or 1, which has a derivative of 0 everywhere except at the origin where it is undefined. This lack of a usable gradient makes optimization using calculus completely impossible. By introducing the sigmoid function, defined as sigma of z equals 1 over 1 plus e to the negative z, we map any input to a smooth value between 0 and 1, yielding a beautiful, continuous S-curve with a clean, computable derivative. Today, we often favor the rectified linear unit, or ReLU, which is simply f of x equals the maximum of 0 or x. ReLU is computationally incredibly cheap, avoids saturating gradients for positive values, and enables modern deep networks to train efficiently without losing signal. When we stack these individual neurons together into layers, something truly magical happens. We feed our inputs into an input layer, which connects to one or more hidden layers, before finally reaching an output layer. In 1989, George Hornick proved the universal approximation theorem, which states that a feed-forward network with a single hidden layer containing a finite number of neurons can approximate any continuous function to arbitrary precision. The hidden layers act as feature extractors, automatically combining low-level inputs into increasingly abstract representations. In image recognition, for instance, the first layer might detect simple edges, the second combines edges into shapes, and the third recognizes complex structures like eyes or noses, all without any human handcrafting these features. To compute the output of an entire layer containing hundreds of neurons, we don't calculate them one by one. Instead, we use linear algebra. We group all our weights into a massive matrix below our activations into a vector A and our biases into a vector B. The activation of the next layer is represented elegantly as the activation function applied to the matrix vector product written as A of L equals sigma of W of L times A of L minus 1 plus B of L. When you hear about modern graphics processing units or GPUs powering the AI revolution, this is exactly what they are doing. They contain thousands of small, specialized cores designed to perform these massive matrix multiplications in parallel, turning what would be hours of EPU computation into mere milliseconds. Before a network can learn, it must have a way to measure how wrong it is. We define this error using a loss or cost function such as mean squared error or categorical cross entropy. If we are training a network to recognize handwritten digits from the MNIST database, we feed it a picture of a 3. If the network outputs high probability for an 8, our cost function penalizes this heavily. The cost C is a function of every single weight bias in the network forming a hyperdimensional landscape. In a modern model with millions of parameters, this landscape is a mind-bending space with countless peaks, valleys, and saddle points, and our goal is to find the absolute lowest point in this vast terrain. To find the minimum of this massive cost landscape, we use an optimization algorithm called gradient descent. Imagine standing on A dark, foggy mountain, and wanting to find the valley floor, you would feel the slope of the ground beneath your feet and take a step in the direction of the steepest descent. Mathematically, we calculate the gradient of the cost function denoted by the vector Nabla-C, which points in the direction of steepest descent, by taking a small step in the opposite direction scaled by a hyperparameter called the learning rate, typically denoted by eta or alpha. We slowly move down the mountain. If the learning rate is too large, we will overshoot the valley entirely. If it is too small, the network will take ages to train or get permanently stuck in a shallow local minimum. The actual engine that calculates this gradient is called backpropagation, and it is entirely powered by the chain rule of calculus. To just awaiting the very first layer of our network based on an error at the final output, we must trace the error backward layer by layer. We compute the partial derivative of the cost with respect to the output, then the output with respect to the pre-activation sum, and finally the sum with respect to the specific weight. This gives us the partial derivative of C with respect to W. By caching these intermediate derivatives and propagating them backward, we avoid redundant calculations, making training feasible. Formulated independently by several researchers, but popularized in 1986 by Rumelhart, Hinton, and Williams, backpropagation remains the mathematical foundation of almost all modern deep learning. For decades, deep networks with more than a few layers simply refused to train due to the vanishing gradient problem. Recall that the derivative of the sigmoid function has a maximum value of only 0.25. As we chain these derivatives together backward through 10 or 20 layers, we are repeatedly multiplying numbers that are less than 1/4. Consequently, the gradient shrinks exponentially as it travels backward, meaning the weights in earliest layers of the network receive almost no update at all and never learn. This critical bottleneck was solved by transitioning to the ReLU activation function, which has a gradient of exactly 1 for all positive inputs, alongside clever weight initialization strategies developed by Xavier Glorot and Kamini. Over the last decade, we have moved beyond simple, fully connected networks to highly specialized architectures. In 1989, Yann LeCun introduced convolutional neural networks, or CNNs, which use shared weight filters to process spatial grid data-like images. In 2017, researchers at Google published the Attention is All You Need paper introducing the transformer architecture, which replaces recurrence with self-attention, mechanisms to process sequential data in parallel. This architectural leap enabled the scaling of models from millions of parameters to hundreds of billions, culminating in modern large language models. What began as a simple mathematical model of a single biological neuron has evolved into massive, distributed digital brains capable of processing, understanding, and generating human-level language and art.